Been a minute, huh, guys? Before we go into anything new, I want to do a quick review in this video on just some basics what we did with solutions, just to try to jog your memory. One of the first things we did was something called a dissociation equation. Don't freak out, it's a lot less complicated than it sounds. If you know how to get chemical formulas, you can easily do dissociation equations. They aren't even chemical reactions quite yet. It's what happens when you add a solid to water and it separates into its components. Let's get started. All you need is a chemical formula for this compound, barium hydroxide. I won't show you that right now. You should know how to get that. When I add it to water, I'm going to show water above this arrow. Simple. What it's going to do, it's going to break apart into its components, the barium ion and the hydroxide polyatomic ion. We know that for that formula to exist, barium would have had to have been a 2+. And see, because it's in column 2, it's going to be a 2+. Hydroxide is a 1- on your chart. And so I know that it is going to break apart into a barium ion of a 2+ and 2 hydroxide ions. Easy. One other thing we've done previously was how to make a solution from a stock concentration. Okay, typically what we have in the chemistry lab is maybe 1 or 2 bottles of something really concentrated, and then depending on what you need, based on whatever needs you have, you can always dilute that using this equation. For this class, almost always, M1 is going to be the stock concentration, 9 times out of 9. And so, typically what you're going to do is usually find V1, which is the volume of concentrate you're going to need to add to get a solution with what you want at a volume that you want. Okay? So I'm just going to rearrange for V1 because I like how it gets me there in one step. So I know that my M1, as my initial molarity, is always 12 molar. My M2 is going to be what I want, 6 molar. And my V2 is going to be the volume that I want, 750 mils. Okay, I'm going to plug that in this equation up here. Sig figs would apply because it is a division and multiplication problem. Okay, I'm going to have to round that up to 2 sig figs to get 380. It's going to make my answer inaccurate, but that's what happens when you don't use sig figs. So that's the milliliters of concentrated stock. The M1V2 manipulation is always going to give you how many milliliters of concentrated stock. Or it could give you liters. For this particular equation, you don't need to change this to liters if you don't want to. I recommend you don't, because a lot of times it's going to be much easier to measure milliliters than it is liters, because a liter is kind of a lot. So we needed 380 milliliters of my concentrated acid. To figure out how much distilled water, all you have to do, simple. Subtract total volume from the volume of concentrated acid that you needed. Now here, you see that when I plug this in, I end up getting 370. Remember that subtraction, it's always the number of sig figs as the number that shows the fewest sig figs to the right of the decimal. These happen to be both, multiples of 10, and they also happen to only have 1 to the end of their, they have no decimal places to the right of the 0 here. So my answer is going to be 370, but if these were different, you would just show none to the right of the decimal. So that's how many milliliters of distilled water I would need. I'm going to skip 6 and 7 just because these are dilutions and easy dimensional analysis. And let's get on to one that's a little bit more challenging, which is the marriage of solution chemistry with some stoichiometry, which means we need a balanced chemical reaction always first. So iron is going to react with hydrochloric acid to make iron 2 chloride, hydrogen gas. You're going to want to balance that. Balanced. Now let's start with my 3.25 grams of iron. You can start with whatever you want. I like this first, and I'll show you why. So I'm going to need to use the molar mass of iron, which, again, it's not going to be tough for you guys. There's iron right there, 55.85 grams per mole. We know from this balanced chemical equation that for every 1 mole of iron, I need 2 moles hydrochloric acid. Now my molarity is going to come into play. This can be tricky. Recall that molarity, capital M, is moles over 1 liter. I can flip and invert that however I want to get the unit cancellation that I need. And for this, I'm actually going to divide by the molarity because I know that I have 3.25 moles of hydrochloric acid for every 1 liter of solution. And so moles is going to go away. And then finally, there are 1,000 milliliters in 1 liter. And this should give me the exact milliliters of acid at that concentration I need to react with that amount of iron in this equation to have a perfect reaction. So 25 divided by 5 times 2 divided by 3.25. I'll need to use, I can use 3 sig figs here, 35.8 milliliters of HCl. Okay, use this to help finish the rest of the worksheet. Check it for points tomorrow.